close your eyes, take a slow, deep breath, and let me take you somewhere very far away, somewhere beyond anything you've ever seen or touched or known. We're going back, all the way back, to the very beginning of everything. 13.8 billion years ago, there was nothing. No stars, no planets, no light drifting through the dark, no sound, no space for sound to travel through, no time ticking quietly in the background, just nothing. And then, in a moment so small it barely deserves to be called a moment at all, everything began. The universe was born. Slowly say that to yourself. Everything began. All the galaxies you've ever seen in photographs, all the mountains and oceans and forests on this earth, all the warmth of every fire ever lit, all the light of every candle ever burned. It all came from that single, quiet, impossible beginning. Scientists call it the Big Bang. But don't let that name fool you. It wasn't loud. It wasn't violent in the way we think of violence. It was more like an awakening, a gentle unfolding, a breath being taken for the very first time. And as you lie here tonight, drifting slowly towards sleep, know that you are made of that beginning. Every atom in your body carries the memory of that first moment. You are as old as the universe itself in the most beautiful way possible. So rest now, rest and know that you came from something extraordinary. And here is something that might surprise you. Something that might make you smile softly in the dark. The Big Bang was not an explosion happening inside space, the way a firecracker bursts open inside a room. No, it was something far more gentle and far more strange than that. It was space itself, expanding, stretching outward the way dough stretches slowly in warm hands. Before the Big Bang, there was no space to explode into. There was no room, no darkness waiting to be filled, no empty stage waiting for the show to begin. Space was created at the very same moment that everything else was created. It grew from nothing into something, gradually and continuously, like a dream filling itself in as you sink deeper into sleep. And even now, as you breathe slowly and your limbs grow heavy against your mattress, space is still expanding. The universe is still stretching. It never stopped. It has been quietly growing for 13.8 billion years, and it is growing still, right now, in this very moment, as you drift closer and closer to sleep. There's something deeply comforting about that, isn't there? The universe never stands still. It never stops becoming something more, and neither do you. Everything that has ever existed, every mountain, every river, every star, every grain of sand on every beach, every thought that has ever passed through a human mind, all of it came from a single point. Scientists call it a singularity. It is perhaps the strangest word in all of science. A singularity is a place where our normal rules break down, where the numbers we use to describe the world stop making sense. The density of this point, the amount of stuff packed into it, was not simply very large. It was, as far as we can calculate, infinite density, infinite temperature, everything compressed into a space smaller than anything you could ever imagine, smaller than a grain of sand, smaller than a speck of dust, smaller than an atom, smaller than the smallest thing you could ever dream. And yet, within that impossibly small point was everything. The material that would one day become your hands, the atoms that would eventually form rivers and clouds and old oak trees, the energy that would become sunlight falling warm across your face on a summer afternoon. It was all there, waiting, quietly, patiently, as if it somehow knew that one day, billions of years from now, a person would lie in a comfortable bed, breathing slowly and drifting into sleep, thinking about where they came from. The temperature at the beginning was not simply hot. It was hot beyond any number that means anything to us in ordinary life. billions of degrees means nothing when you're talking about the first moments of the universe. Scientists describe the temperature at the singularity as effectively infinite. Everything was energy, pure, blazing, formless energy. There was no matter yet, no particles you could point to and name, just heat and light and the raw, undifferentiated stuff of creation, swirling and trembling in that impossibly small space. Try for a moment to imagine the hottest thing you've ever felt, the warmth of a fire on a winter night, the heat of sand under your bare feet on a summer afternoon, the steam rising from a cup of tea resting on your nightstand. Now multiply that feeling 1 trillion times, and then 1 trillion more, and keep going until the numbers stop making sense and you're left only with a vague, warm feeling of awe that is still nowhere near the temperature of the Big Bang. But awe, perhaps, is the right feeling to take into sleep with you. The universe began in something so extraordinarily powerful that our minds simply cannot contain it. And from that unimaginable heat came everything, including you, including this quiet room, including this gentle moment of rest. The name Big Bang has a funny story attached to it, one that might make you smile softly as you settle deeper into your pillow. The man who coined the phrase didn't mean it as a compliment. His name was Fred Hoyle, and he was a brilliant British astronomer who, in the late 1940s, did not believe the universe had a beginning at all. He preferred a different theory, one where the universe had always existed, quietly and steadily, forever. He thought the idea of a dramatic cosmic origin was, frankly, a little ridiculous, and so, during a radio broadcast in 1949, he used the phrase Big Bang somewhat mockingly, the way you might roll your eyes at an idea you find a little too dramatic. But the name stuck. It spread through newspapers and classrooms and late-night conversations, and by the time the evidence for this theory had grown overwhelming, the name had already made itself perfectly at home in the language of science. Fred Hoyle, despite his skepticism, had accidentally given the most important event in the history of the universe its most enduring name. There is something gently ironic about that, something human and humble and a little bit funny. And as you breathe slowly now, your body relaxing into the soft weight of sleep, perhaps you can carry that thought with you, that sometimes even our doubts leave something beautiful behind. The Big Bang theory does not stand on a single piece of evidence, thin and fragile like a single thread. It stands on 3 great pillars, solid and patient as stone. The first is the expanding universe, the observation that galaxies are moving away from us in every direction, exactly as you would expect if everything began from a single point. The second is the cosmic microwave background, a faint, ancient glow of radiation that fills all of space, the leftover warmth of the universe's first great release of light, still drifting softly through the cosmos after nearly 14 billion years. And the third is nucleosynthesis, the fact that the universe contains almost exactly the right amounts of hydrogen and helium that the Big Bang theory predicts, down to fractions of a percent, as if the universe had followed a recipe written in the laws of physics themselves. 3 independent lines of evidence, each one pointing to the same quiet conclusion. The universe had a beginning, a real, datable, describable beginning, and everything that has ever happened, every love story, every thunderstorm, every field of wheat swaying in the wind, every lullaby ever sung to a sleepy child, is a consequence of that beginning. Let that thought settle over you now, like a warm blanket being pulled gently up around your shoulders. Here is something that seems impossible at first, but becomes strangely peaceful when you sit with it long enough. Before the Big Bang, there was no before. Time itself did not exist until the universe began. We are so accustomed to time, the quiet tick of a clock, the slow movement of the sun across the sky, the steady passing of one breath and then another, that it feels as though time must have always been there. waiting, but it wasn't. Time was created along with everything else. It grew out of the singularity the same way space did, the same way matter and energy did. There was no long, dark eternity stretching back before the Big Bang. There was no moment when the universe didn't exist yet, because there were no moments at all. And so the question, what happened before the Big Bang, is, in a very deep and genuine sense, not a question that has an answer. It is like asking, what is south of the South Pole? The question sounds reasonable, but the geography simply doesn't allow for an answer. And somehow, there is rest in that. There is a kind of peace in knowing that the universe has a true beginning, that everything has a starting place, that even time itself once was new. At the very beginning, at the singularity, the laws of physics as we know them simply stop working. Our best equations, the ones we use to describe everything from falling apples to orbiting planets to the bending of light around black holes, they all break down at this single point. The numbers produce infinities, and infinities in physics are usually a sign that something is missing from our understanding. Scientists call this the Planck scale, the smallest possible unit of space and time, where quantum mechanics and general relativity, our two greatest theories of the physical world, begin to contradict each other. It is as if we have two beautiful maps of a country, each one exquisitely detailed, but they describe slightly different versions of the terrain. Whenever you zoom in past a certain point, we are still waiting for a deeper theory, perhaps string theory, perhaps something we haven't imagined yet, that will reconcile those two maps and let us peer even closer to the beginning. But for now, the very first instant of the universe remains a mystery, a quiet, humbling, wonderful mystery. And as you breathe slowly in the dark, drifting toward sleep, perhaps it is enough simply to know that mystery is allowed. That not everything needs to be understood tonight. The Big Bang did not happen at a specific place that you could point to on a map or travel to in a spaceship. It happened everywhere. Every single point in the universe was the Big Bang. The spot above your bed right now, that was the Big Bang. The ground beneath your house, that was the Big Bang. The farthest galaxy, billions of light years away, that was the Big Bang too. Because before the Big Bang, there was no space at all. And as space expanded, every point in it moved away from every other point, the way dots drawn on the surface of a balloon all move away from each other when you blow it up. No dot is the center. No dot is more original than any other. The universe has no center, no edge, no single birthplace that you could travel back to. It began everywhere, all at once, and so you, lying here in this quiet room, are not somewhere on the outskirts of where the Big Bang happened. You are right in the middle of it. You are at the very heart of the universe, in the only sense that matters, because every place is. Let that thought be the last one you carry as you close your eyes a little more. You are not on the edge of anything. You are exactly where you are supposed to be, the very first fraction of a second after the Big Bang. A time called the Planck epoch was stranger than anything that came after it. The temperature was so high and the energy so concentrated that the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were not yet separate. They were unified into a single, undivided force, the way all the colors of light are unified inside a single beam of white light before a prism separates them. The universe was so small and so hot that there was no room for the forces to distinguish themselves. Everything was everything. Energy had not yet become matter. Space had not yet settled into the quiet, expanding geometry we know today. Time ticked in increments so small they have no name in everyday language. It was a world of pure potential, before any particular thing had decided to become what it would eventually be. There is something almost meditative about that image. The world before differentiation, before separation, before any line was drawn between one thing and another, like the moment just before you fall asleep, when thoughts begin to blur at the edges and the boundary between waking and dreaming grows soft and indistinct. That is where the universe began, in that luminous, formless, undivided potential, at about 10 to the power of negative 43 seconds after the Big Bang. A time so small it makes the word instant seem slow and generous. Gravity peeled away from the other forces. It was the first great separation. Before this moment, gravity had been indistinguishable from everything else, tangled together with electromagnetism and the nuclear forces in that single, unified superforce. But as the universe expanded and cooled, even by the tiniest amount, gravity found its own identity. It stepped back from the others and became what it has been ever since. The quiet, patient, inescapable pull that holds planets in their orbits, bends light around stars, and, on a much gentler scale, keeps you lying comfortably in your bed right now, rather than floating away into the dark. Gravity is the oldest of the forces in that sense, the first to find its own shape, and there is something beautiful about that. The force most associated with groundedness, with being held, with the warm weight of your body resting on the earth, was the very first thing in the universe to establish its own identity. So as you feel the gentle pull of the earth beneath you, let it remind you that gravity has been doing this work for nearly 14 billion years, long before the stars, long before the earth, long before you. It has always been here, holding things gently in place. The strong nuclear force, the force that holds the nuclei of atoms together, separated from the others at around 10 to the power of negative 36 seconds. That is still an almost unimaginably small sliver of time after the beginning. But in those first extraordinary fractions of a second, the universe was changing so rapidly that even such tiny intervals were full of meaning and transformation. The strong nuclear force is, as its name suggests, the most powerful force in nature at very short distances. It is what keeps protons and neutrons bound together inside the nucleus of every atom in your body. Without it, every atom would instantly fly apart. The universe would be nothing but scattered particles, never able to combine into anything solid or lasting. It is, in a very real sense, the force of coherence, the thing that makes matter hold together rather than dissolve, and it found its own character at the very dawn of time, before the universe was even a blink of an eye old. By the time it separated from the other forces, the universe was still smaller than anything you could hold in your hand, still blazingly hot, still full of raw, trembling potential. And yet already the architecture of reality was quietly assembling itself, force by force, layer by layer, into the world that you would one day be born into, and in which you are now lying peacefully, ready for sleep. The period called the Grand Unification Epoch is the name scientists give to those extraordinary first moments when three of the four fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, were still unified as one. Only gravity had separated by this point, stepping away into its own identity, while the other three remained intertwined in a single elegant force. This epoch lasted an almost unimaginably brief time, from the very beginning until about 10 to the power of negative 36 seconds, and yet within it, the temperature was so extreme, the energy so concentrated, that the universe bore almost no resemblance to the one we inhabit today. There were no particles as we know them, no protons, no neutrons, no electrons, just raw, seething energy in a space smaller than a single proton. Scientists believe that understanding this epoch, truly understanding it, mathematically and physically, would bring us closer to a grand unified theory of nature, a single beautiful equation that would describe all the forces of the universe as aspects of one underlying reality. We don't have that equation yet, but we are reaching for it. Slowly, patiently, the way you might reach, half asleep, for something just at the edge of a dream. And perhaps, like all the best things, it will come to us quietly when we least expect it. At 10 to the power of negative 36 seconds, something extraordinary happened. The universe, which had been expanding at a rapid but finite rate, suddenly accelerated into an almost incomprehensibly fast expansion called inflation. In a time period so brief, it makes ordinary fractions of a second seem like geological ages. The universe grew by a factor of at least 10 to the power of 26, perhaps far more. To put that in some kind of perspective, imagine taking a single atom and expanding it until it was larger than the observable universe. That gives you some dim sense of how dramatic this inflationary period was. And yet, despite its violence, inflation left the universe remarkably smooth. It ironed out any lumps or wrinkles in the fabric of space, the way a gentle hand smooths a sheet across a bed. It stretched the universe so completely that even the most extreme curves and irregularities in its early geometry were flattened into the near-perfect smoothness we observe today. Inflation is one of the most powerful ideas in modern cosmology, and while we have strong evidence that it occurred, we are still learning the details of exactly what drove it and how it ended. But the image of it, that brief, extraordinary flowering of space, that single vast breath, is one of the most beautiful in all of science. Let it carry you gently towards sleep. During the period of cosmic inflation, the universe expanded faster than the speed of light. This is one of those facts that sounds like it should be impossible, and yet it is entirely consistent with the laws of physics as we understand them. Einstein's theory of relativity says that nothing can move through space faster than light. But it says nothing about space itself. Space is not a thing that moves through anything else. It is the stage on which everything happens, and the stage is allowed to stretch. During inflation, the fabric of space expanded so rapidly that distant regions of the universe were carried apart faster than light could travel between them. This is also why the universe today is so much larger than you might expect given its age. If the universe is 13.8 billion years old, you might think it should be only 13.8 billion light years across. But because space expanded so dramatically, especially during inflation, the observable universe is actually about 93 billion light-years in diameter. The light from the farthest galaxies has been traveling toward us for nearly 14 billion years. But those galaxies are now tens of billions of light-years away, because space between us and them has continued to stretch all that time. The universe is bigger than its own age suggests. It always has been. And there is something quietly wonderful about a universe that is larger than you thought, with more room in it than the numbers first implied. Inflation lasted only until about 10 to the power of negative 32 seconds after the Big Bang. 1/100th of a trillionth of a trillionth of a trillionth of a second, and then it stopped, as suddenly and completely as it began. When inflation ended, the energy that had been driving it was converted into a vast flood of particles and radiation, an event sometimes called reheating, because the rapid expansion of inflation had cooled the universe, and this burst of new particles brought its temperature soaring back up again. The universe was suddenly full of matter and energy in a way it hadn't been before. Particles of every kind flickered into existence, collided, annihilated each other, and reformed. The cosmos was loud with interaction, not with sound, but with the ceaseless exchange of energy and momentum at the smallest scales of reality. And yet, underlying all that frenzy, the universe had been given a shape. Inflation had determined its geometry. It had smoothed out the large-scale structure and embedded within it tiny quantum fluctuations, microscopic wrinkles in the energy density that would one day grow into galaxies and galaxy clusters, and the vast cosmic web of everything. The seeds of your existence were planted in those tiny fluctuations, during an inflationary epoch that ended before the universe was 1 second old. Breathe slowly. Everything that followed was simply those seeds growing. The electroweak force, the unified combination of electromagnetism and the weak nuclear force, existed as a single entity from the beginning of the universe until about 10 to the power of -12 seconds. At that point, as the universe expanded and cooled, these two forces separated the way two colors of paint that have been mixed together can no longer be unmixed once they have dried. This separation is called electroweak symmetry breaking, and it is connected to one of the most celebrated discoveries in modern physics, the Higgs boson. The Higgs field, which permeates all of space, is what gave many particles their mass at this moment of symmetry breaking. Before the Higgs field switched on in this way, fundamental particles were largely massless, racing through the universe at or near the speed of light. Afterward, particles acquired mass, slowed down, and began to behave in the ways we recognize today. Without the Higgs field doing this quiet work, atoms could never have formed. Matter as we know it could never have existed. The discovery of the Higgs boson at the Large Hadron Collider in 2012 was one of the great scientific triumphs of our era, a confirmation rippling back through 14 billion years. The physicists had correctly understood the moment that occurred in the first trillionth of a second of creation. Sleep on that thought. The answers to the universe's oldest questions have been quietly waiting in the mathematics all along. At about 1 microsecond, 1/1,000,000th of a second after the Big Bang, the universe had cooled enough for quarks to combine. Quarks are the smallest building blocks of matter that we know of. Tiny, restless things that never exist alone. In the unimaginable heat of the first microsecond, quarks had been roaming freely in what physicists call a quark-gluon plasma, a hot, dense soup of particles that behaved unlike anything in the universe today. But as the temperature dropped, quarks began to feel the pull of the strong nuclear force more and more powerfully. They found each other. They bound together in groups of 3, forming protons and neutrons, the particles that would go on to become the nuclei of every atom in the universe. This process is called the quark-hadron transition, and it represents another quiet milestone in the universe's long journey from formless energy to structured matter. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 1 up quark and 2 down quarks. And those 2 simple configurations, those tiny, patient arrangements of 3 quarks each, are the foundation of all the matter you have ever seen or touched. The chair beneath you, the pillow under your head, the body breathing slowly in the dark, all of it, at its deepest level, is quarks that found each other in the first microsecond of time. Equal amounts of matter and antimatter were created in the Big Bang. For every particle of matter born in those first fiery moments, an equal particle of antimatter was born alongside it, identical in almost every way, but carrying an opposite charge. When matter and antimatter meet, they annihilate each other completely, converting entirely into energy, into light. And so you would expect that the universe, born with equal amounts of both, would have spent its first seconds in a vast and total annihilation, matter and antimatter cancelling each other out in an endless chain of mutual destruction, leaving behind nothing but light and radiation, no particles, no atoms, no stars, no you. And that is almost what happened. Almost, but not quite. Because for reasons we do not yet fully understand, there was a tiny, tiny imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. Just 1 extra. 1 in a billion. And when the great annihilation was over, when all the antimatter had found its match and vanished in a flash of light, that 1 extra particle of matter in every billion was left behind, unclaimed, surviving. And those survivors, those impossibly outnumbered leftovers, became everything. Every galaxy, every planet, every ocean, every living thing, You are the product of a 1 in a billion imbalance at the beginning of time, and somehow that makes you feel exactly as rare and extraordinary as you are. For every billion antimatter particles in the early universe, there were 1 billion and 1 matter particles. Just one extra piece of matter in every billion, a margin so slim it seems almost accidental, like a miscount. But it was not accidental. It was written into the laws of physics, into the subtle asymmetries of nature, into the deep structure of reality. Scientists call this asymmetry between matter and antimatter CP violation, a violation of the combined symmetries of charge conjugation and parity. In simpler terms, it means that the laws of nature at the deepest level are not perfectly symmetrical between matter and antimatter. Nature has a slight preference, a gentle lean, and that lean, that almost invisible tilt in the balance of the universe, is why anything exists at all. It is one of the most profound and still partly mysterious facts in all of physics. We can observe CP violation in laboratory experiments, in the behavior of certain particles. We can see its fingerprints, but we do not yet have a complete theory that explains why the universe chose this particular amount of asymmetry, why 1 in a billion and not 1 in a trillion or 1 in a million. The answer, when it comes, will be one of the deepest in science. But for now, as you drift into the soft darkness of sleep, simply rest in the knowledge that you exist because the universe was ever so slightly imperfect, and imperfection, it turns out, was exactly what was needed. When matter and antimatter meet, they do not push or pull each other. They simply vanish, completely, instantly, converting entirely into energy, into photons, into light. And in the early universe, this annihilation happened on an almost incomprehensible scale. In those first fractions of a second, the universe was filled with matter and antimatter colliding endlessly, erupting in continuous cascades of light and energy. It was, in a sense, the most dramatic event that has ever occurred. The universe consuming itself almost entirely in a great mutual dissolution. Particle by particle, pair by pair, and then it was over. The annihilation ran its course, and the universe that remained was vastly simpler. Almost all the antimatter was gone. Almost all the matter was gone. What remained was an enormous flood of photons, the light created by all that annihilation, and that small precious surplus of matter, 1 in a billion, that have no antimatter partner waiting for it. Those surviving matter particles, drifting through a universe that was now more light than substance, were the seeds of everything solid that would ever exist. They were the first permanent things, the first things that would not be undone. And as you breathe slowly now, settling deeper into the warmth of your bed, know that you are made of those survivors, the ones that remained when everything else cancelled out. You are what the universe kept. The slight excess of matter over antimatter in the early universe, just 1 extra particle of matter for every billion pairs that annihilated each other, is the reason the universe is made of matter rather than pure energy. This imbalance is called baryogenesis, from the Greek word for heavy particles, the protons and neutrons that make up atomic nuclei. The conditions necessary for baryogenesis were first described by the Soviet physicist Andrei Sakharov in 1967. He identified 3 criteria that must have been met for matter to come to dominate over antimatter. There must have been processes that could change the number of particles. The laws of physics must have treated matter and antimatter slightly differently, and the universe must have been in a state of thermal imbalance, out of equilibrium at some point during this process. All 3 of these conditions appear to have been met in the early universe, but the precise mechanism by which baryogenesis occurred, the exact sequence of events that produced that crucial 1 in a billion surplus, is still one of the great open questions of cosmology and particle physics. It is humbling and wonderful that something as enormous as the existence of all matter in the universe traces back to a process that happened in the first fractions of a second that is still not fully understood, and that left its signature in every atom of your body, breathing slowly there in the dark. The process of matter emerging as the dominant form of substance in the universe, baryogenesis, happened within the first second of the universe's existence. Within 1 second, before the Earth existed, before the Sun existed, before the Milky Way existed, before the first stars had ignited. In that single opening second, the matter that would go on to compose everything was already determined. The universe had made its choice, or rather, the laws of physics had made it for the universe, and matter had won. Antimatter had been almost entirely consumed in its great mutual annihilation with matter, and the photons born from that annihilation now outnumbered the matter particles by roughly 1 billion to 1. The universe was, at this point, mostly light, a vast, brilliant, incredibly hot ocean of radiation, with a thin scattering of matter particles swimming through it, lonely, sparse, but permanent. Those matter particles would spend the next several 100 million years slowly, patiently gathering together under the pull of gravity, cooling, combining, finding each other across the expanding darkness. They would become atoms, then gas clouds, then stars, then galaxies, then planets, then oceans, then life. All from that thin scattering of survivors in the first second of time. Let that quiet fact carry you gently down into sleep. Most of the antimatter annihilation in the early universe was over within the first second of time. 1 second, in human terms, barely a heartbeat. But in cosmic terms, a second is an eternity. When the universe is young and hot and dense enough that particles collide billions of times in the span of a breath, within that single second, the universe had already gone through more transformations than it would undergo in all the billions of years that followed. Forces had separated, quarks had combined into protons and neutrons. Matter had won its asymmetric battle with antimatter. The photons born from that annihilation were already streaming outward in every direction. The universe was already cooling, already expanding, already on its long, slow journey from the blazing heat of creation toward the cool, dark, star-scattered cosmos we inhabit today. And you, in a sense, were already determined. The matter that would one day become you was already there, in that first second, surviving the great annihilation, drifting in a sea of light. You didn't know it yet. The universe didn't know it yet. But the ingredients were present, and the slow, patient work of becoming had already begun. Rest now. Everything that needed to happen has been happening for 13.8 billion years. And it brought you, somehow, exactly here. About 3 minutes after the Big Bang, something remarkable happened. The universe had been expanding and cooling steadily, and by the 3-minute mark, the temperature had dropped to roughly 1 billion degrees. Still unimaginably hot by any human standard, but cool enough, finally, for protons and neutrons to begin sticking together. They were drawn toward each other by the strong nuclear force, and when they met, they held. Protons and neutrons fused, forming the first atomic nuclei. This process is called Big Bang nucleosynthesis, and it is one of the most important events in the history of the universe. Before nucleosynthesis, the universe contained protons and neutrons floating freely in a sea of light and radiation. After nucleosynthesis, it contained the first compound nuclei, the foundations of atoms. The most common product was hydrogen nuclei, which are simply individual protons, unchanged. But some protons and neutrons combined to form deuterium or hydrogen form of hydrogen, and then helium, the second element. A small amount of lithium was also produced. 3 minutes into the life of the universe, and the first chemistry had already begun. The first 2 entries on the periodic table had been written. The raw material of stars, galaxies, planets, and life had been set in place. And as you lie here, breathing slowly, with the whole weight of a long day finally lifting from your body. Remember that the hydrogen in the water that hydrates your cells right now was forged in those first 3 quiet minutes. The universe's first 3 minutes of nuclear activity produced hydrogen and helium in a ratio of roughly 3 to 1 by mass. About 75% hydrogen and 25% helium. And when astronomers go out into the universe today, measuring the composition of ancient stars and primordial gas clouds that have never been enriched by the chemistry of stellar interiors, they find almost exactly that ratio: 75% hydrogen, 25% helium, with tiny traces of deuterium and lithium, precisely what the Big Bang Theory predicts, calculated from the known laws of physics, apply to the conditions of the early universe. This is one of the most beautiful confirmations in all of science, a prediction made from first principles, tested against observations of the universe at its most ancient and unprocessed, and confirmed to extraordinary precision. The universe, in a sense, took careful notes during its first few minutes, and we've been able to read them. This agreement between prediction and observation is not approximate. It is remarkably precise. It means that our understanding of the physics of the early universe is genuinely correct, at least in its broad outlines, and there is something deeply comforting about that. The knowledge that the universe is, at its heart, understandable, that it follows rules, that it left clues, that patient, curious minds have been able to find them. No element heavier than lithium was formed in the Big Bang. Lithium is the third element of the periodic table, a soft, silvery metal. Beyond it, the periodic table stretches on through carbon, oxygen, nitrogen, iron, gold, uranium, and all the rest, the entire rich chemistry of the physical world. But none of those elements existed in the first minutes after the Big Bang. The universe was simply too hot and too short-lived in its nuclear active phase for heavier nuclei to form in significant quantities. The heavier elements had to wait. They had to wait for the first stars to form hundreds of millions of years later. Stars are nuclear furnaces. They spend their lives fusing hydrogen into helium, and then, in their more massive and advanced stages, fusing helium into carbon, oxygen, and heavier elements still. When a massive star exhausts its fuel and explodes as a supernova, it scatters those heavy elements across space, and those scattered elements become the raw material for the next generation of stars, and for planets, and for the chemistry of life. The carbon in your body was forged in a dying star. The oxygen you breathe was blown into space in a stellar explosion. The iron in your blood was created in the core of a massive star that lived and died long before the Earth existed. You are quite literally made of stardust. And it all traces back to a universe that began with just hydrogen and helium 3 minutes after the beginning of time. Big Bang nucleosynthesis. The brief period of nuclear fusion that produced the first hydrogen, helium, and lithium lasted only about 20 minutes. 20 minutes. Then it was over. The universe had expanded and cooled to the point where nuclei could no longer fuse. The temperature was no longer high enough to overcome the electrical repulsion between positively charged protons. The window for primary nucleosynthesis had closed, and the universe settled into a long, quiet phase where nothing dramatic would happen for hundreds of thousands of years. Nuclei drifted through a hot plasma of electrons and photons. The universe was still opaque to light. Photons could not travel freely because they were constantly bouncing off the sea of free electrons. It was a universe that, for all its drama in the first minutes, had settled into a kind of warm, blowing stillness, like a fire that has burned down from its fierce first blaze into a steady, patient glow. Still hot, still luminous, but no longer changing rapidly, simply expanding, slowly cooling, waiting. And there is something peaceful about that image. The young universe, after all the drama of its first moments, simply resting for a while in its warm, luminous haze, letting time do its quiet work. As you rest now, as you let the day's noise and motion settle, as you simply breathe and wait for sleep to come, deuterium is a form of hydrogen with an extra neutron in its nucleus. Ordinary hydrogen has just a single proton, the simplest atom in existence. But deuterium has a proton and a neutron bound together, making it twice as massive and subtly different in its chemistry. It is sometimes called heavy hydrogen, and water made with deuterium instead of ordinary hydrogen is called heavy water. Deuterium was produced during Big Bang nuclear synthesis, forged in those first 20 minutes, and unlike the heavier elements, it is not easily made in stars. In fact, stars tend to destroy deuterium rather than create it, fusing it into helium in their interiors. This means that almost all the deuterium in the universe today is primordial. It dates back to the Big Bang, and by measuring how much deuterium exists in the oldest, most unprocessed parts of the universe, cosmologists can actually test their models of what conditions were like in those first minutes. Deuterium is, in a sense, a fossil of the early universe, a record, preserved in its very existence, of the temperature and density of the cosmos when it was less than 20 minutes old. The universe left clues about its own beginning, scattered across the periodic table, waiting in the nuclei of atoms for patient scientists to find them. And find them they did. What a quiet miracle that is. The abundance of light elements, hydrogen, helium, deuterium, and lithium in the universe is one of the three pillars of evidence for the Big Bang. It is remarkable not just that these elements exist in the right proportions, but that the proportions are sensitive to conditions in the early universe in ways we can actually calculate. The density of ordinary matter in the early universe, for example, directly affects how much deuterium and helium were produced. If the universe had been slightly denser, there would be more helium and less deuterium. If it had been slightly less dense, there would be less helium and more deuterium. By measuring the actual abundances of these elements in the oldest astronomical objects, ancient stars, distant gas clouds, quasar absorption lines, cosmologists can effectively take the temperature and density of the universe when it was 20 minutes old, and those measurements are consistent, not just with each other, but with the measurements we get from the cosmic microwave background and from the large-scale structure of the universe. Three completely independent ways of measuring the early universe, all pointing to the same answer. Science at its most beautiful. Different roads, all leading to the same quiet truth. Let that convergence of evidence be a comfort to you as you settle into the dark. Some things really are known. Some questions really do have answers. After the brief, brilliant period of nuclear synthesis ended, after those first 20 minutes of nuclear fusion had produced the universe's supply of hydrogen, helium, and a whisper of lithium, the universe entered a long, quiet phase that would last for about 380,000 years. It was still hot. It was still far too hot for electrons to settle into orbits around nuclei. The temperature was thousands of degrees, roughly the temperature at the surface of the sun today, and at those temperatures, atoms simply cannot exist. Any electron that was briefly captured by a nucleus would almost immediately be knocked loose again by a high-energy photon. The universe was a plasma, a hot, electrically charged gas of bare nuclei and free electrons, dense enough that light could not travel more than a short distance before being scattered. The cosmos was opaque. If you had been there, and you most certainly were not, but imagine, you would have been surrounded by a uniform, brilliant glow in every direction. Not darkness, but an all-encompassing luminosity that revealed nothing, because photons could not carry information about their origin through that dense, scattering sea. It was a universe full of light, and yet effectively blind. A universe waiting patiently for the temperature to fall just enough for something new to become possible, like a long, warm breath being held, like the moment before sleep when the mind is still full of light and thought, just before everything goes quiet and still. About 380,000 years after the Big Bang, the universe crossed a threshold. The temperature had dropped to about 3,000 degrees, still very hot but cool enough, finally, for electrons to be captured by nuclei and stay there. Hydrogen atoms formed, helium atoms formed. The plasma that had filled the universe since the beginning, that hot, electrically charged sea of free particles, finally became a neutral gas. This event is called recombination, though the name is slightly misleading, since electrons had never been combined with nuclei before. This was the first time, but the name stuck, and what it describes is genuinely beautiful. At the moment of recombination, the universe became transparent. For the first time, photons could travel freely through space without constantly bouncing off free electrons. Light was released. The universe, which had been opaque and glowing for 380,000 years, suddenly became clear, and photons that had been trapped in that dense plasma streamed outward in all directions. Those photons are still traveling today. They fill all of space. We call them the cosmic microwave background. And when you look up at a clear night sky, somewhere out beyond the stars, beyond the galaxies, those ancient photons are still drifting, still moving, still carrying the memory of the moment the universe first opened its eyes. The light released at the moment of recombination, that ancient flood of photons that streamed out when the universe first became transparent, is what we observe today as the cosmic microwave background, or CMB. It is everywhere. It fills all of space, coming from every direction with almost equal intensity. It is the oldest light in the universe, a direct snapshot of what the cosmos looked like 380,000 years after the Big Bang, when the universe was still only a tiny fraction of its current age. In the nearly 14 billion years since it was released, this light has been stretched by the expansion of the universe. The photons that were once in the visible and infrared range, like the glow of warm embers, have been redshifted all the way down to microwave wavelengths. Their temperature, once about 3,000 degrees, has cooled to just 2.725 degrees above absolute zero. They are almost imperceptibly cold now, almost perfectly uniform, almost silent, but they are there, and they carry within them, in the faintest variations from one part of the sky to another, the imprint of the tiny density fluctuations that would one day grow into galaxies. The CMB is the universe's earliest baby picture, faded with age, stretched by expansion, but still remarkably clear and informative to those who know how to read it. You are, in this moment, being gently bathed in that ancient light. It passes through you as you sleep. After the moment of recombination, when atoms had finally formed and the universe had become transparent, the cosmos entered what astronomers call the cosmic dark ages. It is perhaps the most evocative name in all of cosmology. The Dark Ages were a period lasting from roughly 380,000 years after the Big Bang to somewhere between 150 and 800 million years, during which the universe contained no stars, no galaxies, no sources of visible light at all. There was matter, hydrogen and helium gas, slowly drifting through the expanding darkness. There was the faint afterglow of the CMB, cooling steadily as the universe grew. And there was dark matter, whose gravity was quietly, invisibly pulling that gas into filaments and clumps. But there was no fire, no light in the visible sense. The universe was dark in a way it has never been since. A vast, cool, featureless sea of gas, expanding and cooling in the silence between the end of one era and the beginning of another. There is something strangely peaceful about the image, once you allow yourself to sit with it. The universe, after all the drama of its first moments, entering a long and quiet rest, a period of gestation, of slow preparation. The darkness before the dawn. Just as sleep sometimes is the dark and quiet period before a new day of becoming. Rest in the dark, let the quiet do its work. The cosmic dark ages lasted for roughly 150 to 800 million years, though the precise boundaries are still being studied. During this time, the universe was not entirely static. Far from it. Beneath the darkness, gravity was doing its slow and patient work. The tiny fluctuations in density that had been imprinted on the universe at the moment of recombination, those microscopic variations in how much matter was in one region versus another, were growing. Regions that were slightly denser than average pulled in more matter from their surroundings. They grew denser still. More matter fell in. Over millions of years, these overdense regions gathered into large structures, filaments of gas and dark matter, stretching across the expanding universe like a vast, invisible web. At the densest intersections of these filaments, matter piled up in great concentrations. Gas clouds formed, grew larger, began to collapse under their own gravity, and at some point, perhaps 200 million years after the Big Bang, perhaps a little later, the first of these collapsing gas clouds grew dense and hot enough at its core to ignite. The first star was born. A fierce, brilliant, short-lived thing, 100 times more massive than the sun, burning with a blue-white fury. And the Dark Ages ended. Light returned to the universe, slowly, one star at a time. Like candles being lit, one by one, in a room that has been dark for a very long time. As the universe drifted through the cosmic Dark Ages, hydrogen gas slowly clumped and gathered under the gentle, persistent pull of gravity. This process was neither fast nor dramatic. It unfolded over tens and hundreds of millions of years, an almost incomprehensibly slow accumulation, atom by atom, cloud by cloud, filament by filament. The gas that had been released at recombination was mostly smooth and uniform, but not perfectly so. There were tiny variations, density fluctuations of roughly 1 part in 100,000, imprinted by quantum processes in the earliest moments after the Big Bang. These were the seeds, and gravity, patient and inexorable, amplified them. Regions that were just slightly denser than average had just slightly more gravitational pull. They attracted just slightly more gas from their surroundings, which made them denser still, which gave them more pull, which brought in more gas. A feedback loop running over millions of years in the cool dark of an empty universe. This is how structure forms in the cosmos, not through sudden dramatic events, but through the quiet, slow, compounding work of a single force. The same force that holds your body gently against the earth right now, keeping you from floating away, reminding you with this patient weight that you are here, grounded, present. Gravity has always been the architect of the large-scale universe, the builder who works slowly, never rushing, but always building. The first stars in the universe are called population 3 stars, and they were unlike any stars that exist today. They formed from pure hydrogen and helium, the only elements available in the early universe, and they contain none of the heavier elements that enrich the stars we see today and the sun that warms our Earth. Because of this purity, population 3rd stars behaved differently from their later successors. They were, on average, far more massive, perhaps 100 or even 1,000 times the mass of the sun, and because massive stars burn hotter and faster, they lived extraordinarily brief lives by stellar standards. Some burned through their fuel in just a few million years, a cosmic eye blink. Then they collapsed and exploded in tremendous supernovae, scattering their interiors across space. And here is the beautiful part. The interiors of these first stars, forged in stellar nuclear fusion, contained heavier elements: carbon, oxygen, nitrogen, silicon, iron. Elements that had not existed in the universe before. Elements that were now, for the first time, seeding the cosmos. The next generation of stars formed from gas clouds enriched with these heavier elements. And the generation after that was richer still. each stellar generation adding to the chemical complexity of the universe, building slowly toward the conditions that would one day allow rocky planets, liquid water, and the remarkable chemistry of life. The formation of the first stars, the population 3 stars that lit up the universe after the cosmic dark ages, is connected to a process called reionization. During the dark ages, the hydrogen gas that filled the universe was neutral. Electrons were bound to protons, forming stable atoms. But when the first stars ignited, they emitted enormous amounts of ultraviolet light. And ultraviolet light, when it strikes a neutral hydrogen atom, has enough energy to knock the electron free, to ionize it. As more and more stars formed and burned, their combined ultraviolet radiation began to ionize the surrounding gas. The process spread outward from the first stars like ripples from stones dropped in a still pond, bubbles of ionized hydrogen expanding and merging, until eventually the entire universe had been reionized. The dark ages were truly over. The universe was filled with light, and with the warm ionized gas of a cosmos in full stellar activity. Reionization is thought to have been largely complete by about 1 billion years after the Big Bang. We can observe its effects in the light from distant quasars, which shows the telltale signatures of hydrogen absorption from the neutral gas of the dark ages. And the James Webb Space Telescope is now probing this era directly, watching the first galaxies light up the ancient dark with its extraordinary vision. The universe is not finished telling its story. We are still learning to read it. The cosmic microwave background, the faint, ancient glow of radiation that fills all of space, was accidentally discovered in 1965 by 2 American radio astronomers named Arno Penzias and Robert Wilson. They were working at Bell Telephone Laboratories in New Jersey using a large horn-shaped radio antenna that had been built to communicate with satellites. When they pointed it at the sky, they detected a persistent, annoying hiss, a background noise coming equally from every direction, no matter where they pointed the antenna. They checked everything. They cleaned the antenna. They removed what they would later diplomatically describe as white dielectric material, meaning pigeon droppings, from the inside of the horn. The noise remained. It came from everywhere. It was constant, and it corresponded to the thermal emission of something at a temperature of about 2.7 degrees above absolute zero, almost by accident. Almost despite themselves, they had detected the afterglow of the Big Bang itself, the oldest light in the universe, drifting through their antenna on a quiet afternoon in New Jersey. They were awarded the Nobel Prize in Physics in 1978 for this discovery, which was perhaps the single most powerful confirmation of the Big Bang theory. And there is something deeply human and wonderful about the story, that one of the greatest discoveries in the history of cosmology came from 2 men trying to figure out why their antenna was making an annoying noise. The cosmic microwave background radiation has a temperature of approximately 2.725 degrees Kelvin. That is 2.725 degrees above absolute zero. The coldest possible temperature, the point at which all molecular motion ceases. In more familiar terms, it is roughly negative 270 degrees Celsius or negative 454 degrees Fahrenheit. Unimaginably cold, the CMB permeates all of space. It is literally everywhere, a faint whisper of warmth drifting through the universe, a memory of the brilliant light released when the cosmos first became transparent. In the roughly 13.8 billion years since recombination, the expansion of the universe has stretched these photons to longer and longer wavelengths, cooling them steadily from the 3,000 degrees they had at birth to this whisper of a temperature today. If the universe continues to expand, and all evidence suggests it will forever, the CMB will continue to cool. In trillions of years, it will approach absolute zero asymptotically, growing colder and colder, stretched thinner and thinner across an ever vaster expanse of space. It will never quite reach absolute zero. It will simply fade. But for now, it is present, measurable, tangible in its data, right now. As you breathe slowly and the night is quiet around you, photons from the Big Bang are passing through your body. They always are, ancient, cold, and full of information about the very beginning of everything. The cosmic microwave background is remarkably uniform. Look at the CMB from one direction in the sky, and then look at the opposite direction. Regions so far apart that no signal could ever have traveled between them in the age of the universe. And the temperature is the same to 1 part in 100,000. This uniformity is extraordinary. It suggests that the early universe was extraordinarily smooth and well mixed, with barely a ripple in its distribution of temperature and density. But here is the puzzle. How could regions of the universe that have never been in contact with each other end up at precisely the same temperature? In ordinary physics, things come to the same temperature by exchanging heat, by being in contact, by interacting. But those distant regions of the CMB have never interacted. The universe has not been around long enough for light to travel between them. And yet they are the same. This puzzle is called the horizon problem, and it is one of the key motivations for the theory of cosmic inflation. If the universe underwent a period of extremely rapid expansion in its first moments, then regions that are now far apart were once extremely close enough to have been in thermal contact, to have equalized their temperatures before being separated by inflation's sudden vast expansion. Inflation solves the horizon problem elegantly. And the near-perfect uniformity of the CMB is the quiet evidence that it did. The tiny fluctuations in the CMB, those almost imperceptible variations of 1 part in 100,000 from one point in the sky to another, are among the most important patterns in all of science. They are the direct imprint of quantum fluctuations in the early universe, amplified by inflation into variations in the density of matter and energy. And those density variations are the seeds of everything. Where the CMB is very slightly warmer than average, matter was slightly denser at the time of recombination. And where matter was slightly denser, gravity was slightly stronger. And where gravity was slightly stronger, matter accumulated over time. Over hundreds of millions of years, those slight overdensities grew into filaments and sheets and clusters of galaxies. The vast cosmic web of large-scale structure that fills the universe today. Every galaxy in the sky, including the Milky Way, including the unremarkable spiral arm where our sun resides, including the small rocky planet where you are lying in bed right now, traces its origin to one of those tiny ripples in the CMB, a quantum fluctuation stretched by inflation, recorded in the temperature of ancient light, grown over billions of years into a galaxy, into a star, into a planet, into a person lying quietly in the dark, breathing slowly, asleep. The COBE satellite, the Cosmic Background Explorer, was launched in 1989 and was the first spacecraft to map the cosmic microwave background in detail. Before COBE, we knew the CMB existed and we had measured its overall temperature, but COBE revealed for the first time the faint variations across the sky, those tiny temperature fluctuations of 1 part in 100,000 that encode the seeds of all cosmic structure. The discovery was so significant that the scientists who led the COBE project, George Smoot and John Mather, were awarded the Nobel Prize in Physics in 2006. Stephen Hawking called it the scientific discovery of the century, if not of all time. And the image that COBE produced, an oval map of the whole sky, speckled with the faintest variations of color, warm and cool by tiny fractions of a degree, became one of the most iconic images in the history of science. It was a portrait of the universe as it was 380,000 years after the Big Bang, a baby picture of the cosmos. Every subsequent CMB satellite, WMAP in 2001, and then Planck in 2009, refined that picture further, adding detail and precision, until we now have a map of the early universe of extraordinary clarity. We have taken a photograph of the universe at the age of 380,000 years, and we have used it to measure the age, composition, and geometry of everything that exists. The Planck satellite, operated by the European Space Agency, was launched in 2009 and observed the cosmic microwave background until 2013. It produced the most detailed map of the CMB ever made, a picture of the early universe at a resolution and precision that would have seemed like science fiction just a generation earlier. From Planck's data, cosmologists were able to extract an extraordinary amount of information about the universe. The age of the universe, 13.8 billion years, measured to an accuracy of less than 1%. The composition of the universe, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. The geometry of the universe, almost perfectly flat, meaning that space on large scales curves neither toward itself like the surface of a sphere, nor away from itself like a saddle. The amplitude of the primordial fluctuations, the spectrum of those fluctuations, even the number of neutrino species, all of this information extracted from the faint cold glow of ancient light drifting through every corner of space. The Planck satellite stared at the oldest light in the universe and read in it a detailed biography of everything. It is one of the great achievements of human science, patient, precise, humbling in the depth of what it reveals. And as you drift towards sleep, warmed by your blankets, you might spare a thought for those ancient photons, still traveling, still whispering, still full of secrets. The cosmic microwave background was predicted before it was ever observed by a pair of physicists named Ralph Alpher and Robert Herman in 1948. Working from the theoretical framework of the Big Bang model, they calculated that if the universe had begun in a hot, dense state and had been expanding ever since, there should be a residual glow of radiation filling all of space. A thermal afterglow from the era before the universe became transparent. They even estimated its temperature at roughly 5 degrees Kelvin, which turned out to be reasonably close to the measured value of 2.725 degrees. But their prediction was largely ignored. The technology to detect such faint microwave radiation did not yet exist, and the theoretical community was not yet fully persuaded by the Big Bang model. Alpha and Herman's prediction sat quietly in the scientific literature for 17 years, until Penzias and Wilson accidentally stumbled upon the signal with their antenna in New Jersey. When the connection was made, when theorists pointed out that what Penzias and Wilson had found was exactly what Alpha and Herman had predicted, it was one of those beautiful moments when the power of human reasoning becomes undeniable. The universe had been predicted to have this particular gentle afterglow. And there it was, right where the math said it would be, waiting patiently for someone to listen. Edwin Hubble, working at the Mount Wilson Observatory in California in the 1920s, made one of the most consequential observations in the history of science. He measured the distances to several galaxies, then called nebulae, and compared those distances to how fast those galaxies were moving away from us, as revealed by the red shift of their light. What he found was a clear and striking pattern. The farther a galaxy was, the faster it was receding. Galaxies twice as far away were moving twice as fast, 3 times as far, 3 times as fast. This relationship, now called Hubble's law, implied something extraordinary. It meant that the universe was expanding. Everything was moving away from everything else. The way raisins in a rising loaf of bread all move away from each other as the dough expands. And if everything was moving apart today, then in the past, everything must have been closer together. Run the expansion backward like rewinding a film, and everything converges toward a single point at a single moment. The discovery of the expanding universe was, more than any other single observation, the empirical foundation of the Big Bang theory. It was the first great clue that the universe had a beginning, and Hubble found it by patiently measuring the light of distant galaxies, one by one, through a telescope on a California mountain under the cold, clear stars. The rate at which the universe is expanding is described by a number called the Hubble constant. It tells us how fast distant galaxies are receding per unit of distance, currently estimated at roughly 70 kilometers per second per megaparsec, though there is an ongoing and fascinating scientific debate about its precise value. The Hubble constant has been one of the most important and most contested numbers in cosmology for decades. It affects our calculation of the age of the universe, the size of the observable universe, and the history of cosmic expansion. In recent years, two different ways of measuring it, one using observations of the CMB and one using observations of supernovae and other distance indicators, have given slightly different answers, a discrepancy known as the Hubble tension. This tension may reflect a real gap in our understanding of the universe, or it may eventually be resolved by better measurements. Either way, it keeps some of the world's best cosmologists awake at night, metaphorically of course, while you lie here drifting gently towards sleep. There is something reassuring about the fact that even our deepest understanding of the cosmos still has open questions. Science is not finished. The universe still has things to teach us, and every unresolved tension is an invitation, quiet and patient, to look more carefully, to measure more precisely, to understand more deeply. The expansion of the universe does not mean that galaxies are flying through space away from us, like balls thrown outward from an explosion. It means that space itself, the fabric of the cosmos, is stretching. The galaxies are, in a sense, sitting still while the space between them grows. This is a subtle but important distinction. It means that there is no center of expansion, no place where the Big Bang happened that everything is fleeing from. Every point in the universe sees every other point moving away from it because the space between them is growing everywhere at once. An observer in a distant galaxy would look out and see our galaxy receding, just as we see theirs receding. No one is at the center. No one is at the edge. The universe is not expanding into anything. There is no empty space waiting to be filled beyond the edge of the universe. Space itself is what's growing. The universe is all there is, and all of it is stretching, like the surface of an inflating balloon. And because space stretches, light traveling through it gets stretched too, its wavelength growing longer, its color shifting toward the red end of the spectrum. This red shift is what Hubble measured in distant galaxies. It is the signature of an expanding universe, written in the color of starlight, waiting to be read. In 1998, two independent teams of astronomers made a discovery that overturned everything cosmologists thought they knew about the long-term fate of the universe. They were studying a particular type of exploding star, a type Ia supernova, that can be used as a precise distance marker because every such supernova reaches almost exactly the same peak, brightness. By comparing how bright these supernovae appeared with how far away they were, the teams hoped to measure how the expansion of the universe was slowing down over time. Because it was slowing down, wasn't it? Gravity, acting on all the matter in the universe, should be gradually pulling everything back together, decelerating the expansion. That was the expectation. What they found instead was shocking. The distant supernovae were fainter than expected, meaning they were farther away than they should be if the expansion were slowing down. The expansion of the universe was not decelerating, it was accelerating, getting faster over time. This was not supposed to happen. It implied that something was pushing the universe apart, some form of energy uniformly distributed throughout space with a repulsive effect. We call it dark energy. We know almost nothing about what it actually is, but it makes up roughly 68% of everything in the universe. And because of it, the universe will expand forever, getting larger and colder and emptier with each passing age. The acceleration of the universe's expansion, driven by dark energy, is one of the most profound and unsettling discoveries in the history of cosmology. Dark energy is not a substance in the ordinary sense. It does not clump. It does not interact with ordinary matter in any way we can detect directly. It simply pushes. Uniformly throughout all of space, at every point in the universe, dark energy exerts a repulsive pressure that drives space to expand faster and faster over time. It was first proposed by Einstein himself, not under that name, but as a cosmological constant in his equations of general relativity, a term he added to produce a static universe. He later abandoned it, calling it his greatest mistake. But when dark energy was discovered observationally in 1998, cosmologists realized that Einstein's cosmological constant, his greatest mistake, was actually the best available mathematical description of this mysterious force. The constant he added to prevent expansion turned out to describe the very thing causing the observed acceleration. There is something wonderfully ironic about that, something human and humbling. The greatest physicist of the 20th century made a mistake that turned out to be correct for the wrong reason, in a way he would never have imagined. Science, like life, rarely proceeds in a straight line. Dark matter makes up approximately 27% of the total energy content of the universe, and despite decades of study, we have never directly detected a single dark matter particle. We know it exists because of its gravitational effects. Galaxies rotate faster than they should if they only contain the visible matter we can see: stars, gas, and dust. The extra rotation speed implies the presence of an enormous halo of invisible matter surrounding every galaxy. Galaxy clusters bend light more strongly than their visible mass can account for. Another sign of dark matter: the large-scale structure of the universe, the cosmic web of filaments and voids, matches computer simulations precisely only when dark matter is included. The evidence is overwhelming and consistent across many independent observations. But we don't know what dark matter is made of. It doesn't emit light, absorb light, or interact with ordinary matter except through gravity. It passes through planets, through people, through detectors, without leaving a trace. Right now, as you lie in bed, dark matter is drifting through you, through the walls, through the earth, at some unknown rate, leaving no impression at all. You will never feel it, and yet without it, galaxies would not have formed. Stars would not have ignited. The universe would be a thin, formless sea of hydrogen gas, and you would not be here to wonder about it. Ordinary matter, the kind that makes up stars, planets, people, oceans, air, everything you have ever seen or touched, constitutes only about 5% of the total energy content of the universe. Just 5%. The rest is dark energy, 68%, and dark matter, 27%. The universe, it turns out, is mostly made of things we have never seen and do not yet understand. All of human civilization, all the mountains and valleys of the earth, all the stars in the night sky, all the galaxies in the observable universe, they are all just the thin, luminous froth on the surface of something vast and invisible and barely understood. This is perhaps the most humbling fact in all of science. We've spent centuries learning to understand the world around us, and we have done remarkably well. We have mapped atoms and stars and galaxies. We have understood forces and particles and fields, and yet all of that, all of it, accounts for only 5% of what actually exists. The universe has 3 major components, and we only really understand one of them. The other 95% remains a profound mystery, and there is something both unsettling and beautiful about that. The universe still has most of itself left to reveal. We are early in the story. We are still, in a deep and literal sense, just beginning to understand where we are. Georges Lemaitre was a Belgian Catholic priest and physicist who, in 1927, was the first to propose that the universe was expanding. He derived his expanding universe solution independently from Einstein's equations of general relativity before Hubble's observational confirmation in 1929. He called the initial state of the universe the primeval atom, or the hypothesis of the primeval atom, a single, dense, hot state from which everything expanded, Lemaitre was, in many ways, the true intellectual father of what we now call the Big Bang Theory. He was a deeply thoughtful and humble man, and he was careful to separate his scientific work from his religious beliefs, insisting that the Big Bang was a scientific hypothesis to be tested by evidence and was not a statement about creation in the theological sense. Einstein initially dismissed Lemaitre's expanding universe solution as mathematically correct but physically abhorrent. He later came to embrace it and reportedly told Lemaitre, "This is the most beautiful and satisfying interpretation of creation to which I have ever listened." A priest and a physicist, a Belgian and a German, a man of faith and a man of science, together arriving at the beginning of the universe. There is something quietly moving about that collaboration, something that speaks well of what human minds can do when they work honestly toward the truth. If you could run the expansion of the universe backward, if you could reverse every galaxy's motion, pull all the matter of the cosmos back toward itself, rewind the film of cosmic history, you would eventually reach a moment when everything was in the same place, a moment of infinite density and infinite temperature, a singularity. This is the mathematical conclusion of applying Einstein's general relativity to the observed expansion of the universe. Run the universe backward, and it converges. Run it backward to the very beginning, and it converges to a point. This is the theoretical heart of the Big Bang Theory. It is not a hypothesis invented out of thin air or philosophical preference. It is the unavoidable mathematical consequence of the fact that the universe is expanding today. If it's expanding now, it was smaller in the past. If it was smaller, it was denser and hotter. Continue that reasoning to its logical conclusion, and you arrive at the singularity, the beginning, the moment when our equations give out and our understanding runs dry. The place where the map ends and the territory begins, and every night in the darkness, you are at the far edge of a universe that began at that point. 14 billion years of expansion, of cooling, of stars being born and dying, of galaxies forming and drifting apart, and here you are at the outermost edge of all that becoming, breathing slowly, nearly asleep, safe at the end of a very long journey. The steady state theory was the Big Bang's main rival for much of the 20th century. Proposed in 1948 by Fred Hoyle, Thomas Gold, and Hermann Bondi, it described a universe that had no beginning and no end. A universe that was expanding, yes, but in which new matter was continuously being created to fill the gaps left by expansion, keeping the universe's average density constant over time. It was, in its own way, a beautiful theory, elegant, philosophically appealing, and deeply resistant to the idea of a cosmic origin. Hoyle, in particular, spent decades arguing for it with great intelligence and passion. But the evidence, over time, simply did not support it. The cosmic microwave background, a prediction of the Big Bang with no natural explanation in the steady-state model, was the decisive blow. The steady-state theory, by the mid-1960s, had become untenable. Most cosmologists abandoned it. Hoyle never fully did, continuing to propose alternative explanations for the CMB until his death in 2001. He was, by many accounts, one of the most brilliant astrophysicists of his generation, a man whose contributions to the theory of stellar nuclear synthesis, how elements are forged in stars, were Nobel-worthy but were passed over for the prize. He was right about many things and wrong about the steady state, but his willingness to argue for an unpopular position and his tenacity in defending it are part of what makes the history of cosmology so vivid and human. The oscillating universe theory, also called the cyclic model, proposes that the universe does not simply expand forever, but instead eventually stops, contracts under its own gravity in a big crunch, and then bounces back in a new Big Bang. The universe in this picture is not a one-time event, but an eternal cycle, breathing in and breathing out, expanding and contracting, beginning and ending and beginning again. endlessly. It is a deeply appealing idea with a kind of mythological resonance. The universe as a beating heart, a pulsing breath, an eternal repetition. And some versions of cyclic cosmology, developed more recently using the mathematics of string theory and brain collisions, are genuine scientific proposals, not mere poetry. However, the discovery of dark energy, the fact that the universe's expansion is accelerating rather than slowing, makes the classical oscillating model very difficult to sustain. If the universe is accelerating, it will never contract. It will expand forever. The Big Crunch, in the simpler sense, appears to be off the table, but modern cyclic models such as the ekpyrotic model developed by Paul Steinhardt and Neil Chirok propose cycles that don't require a crunch versions, where the Big Bang is a recurring collision between higher dimensional membranes. The conversation is still open. The universe's long-term fate is still, in its deepest sense, unknown. And as you drift towards sleep, perhaps that openness, that sense of a story still unfinished, is itself a kind of comfort. The multiverse is one of the most extraordinary ideas in modern cosmology, and also one of the most controversial. It proposes that our universe, with its particular laws of physics, its particular values of fundamental constants, its particular history, is not the only universe. It is just one of an enormous, perhaps infinite number of universes, each potentially with different laws, different constants, different structures, different possibilities. Our Big Bang, on this view, was not the Big Bang, the origin of everything, but a Big Bang, one of countless such events, each inflating its own bubble of space-time, each following its own version of the laws of nature. Some of these universes might be lifeless and featureless. Some might have structures we can barely imagine. Some might have versions of you living slightly different lives, making slightly different choices, under stars that formed from slightly different physical laws. The multiverse hypothesis is difficult to test experimentally. By definition, other universes are not accessible to our observations, but it arises naturally from the mathematics of inflation, and it is taken seriously by many physicists. Whether or not it is true, it is a profound expansion of the imagination. It invites us to consider that what we call the universe might be just one small chapter in a story of incomprehensible vastness. Close your eyes and let that vast, quiet possibility carry you gently into sleep. String theory and loop quantum cosmology are two of the leading attempts to extend our understanding of physics beyond the point where our current theories break down at the singularity of the Big Bang. String theory proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating one-dimensional strings of energy. Different vibration modes of these strings correspond to different particles. In string theory, the universe has more than the 4 dimensions we experience, typically 10 or 11 dimensions, with the extra ones compactified into spaces so small they are invisible to current experiments. Loop quantum cosmology, on the other hand, proposes that space itself is made up of discrete, quantized loops, that there is a smallest possible unit of space, below which the concept breaks down, the way there is the smallest unit of energy in quantum mechanics. Both of these theories predict in their own ways that the singularity at the beginning of the Big Bang was not truly infinite, that quantum effects smooth it out, preventing the density and temperature from actually reaching infinity. In some loop quantum cosmology models, the Big Bang is actually a big bounce, a rebound from a previous collapsing universe. The universe didn't begin from nothing, it collapsed, bounced, and expanded again. A cycle of becoming, stretching back through time in a chain we cannot yet trace. Brain cosmology, sometimes called the ekpyrotic model, is one of the more exotic ideas in modern theoretical physics, and one of the most evocative. It draws on the mathematics of string theory and proposes that our universe is a 3-dimensional membrane, a brain floating in a higher dimensional space called the bulk. In this picture, there may be other brains nearby, parallel universes drifting through the bulk like sheets of paper floating a hair's breadth apart. And the Big Bang in this model was not a creation from nothing. It was a collision. Two brains drifted together, touched, and the energy of their collision was converted into the hot, dense state we call the Big Bang. The universe was not born from a singularity, but from a cosmic impact, the way a spark is born from two stones striking each other. After the collision, the brains rebounded and separated, and our universe expanded outward from the region of impact. This model elegantly avoids the singularity. There is no moment of infinite density. There is only a collision between extended objects, and it offers a natural explanation for why the universe is so uniform. Because the brains, before they collided, had time to equalize their temperature and density. It is a theory that will require years, perhaps generations, to test. But it is a beautiful example of how physics, at its most creative, dares to imagine realities completely beyond everyday experience. What caused the Big Bang? It is perhaps the most fundamental question in all of science, and the most honest answer at this moment in human understanding is, we don't know. We can describe what happened after the Big Bang with extraordinary detail and precision. We can trace the universe's history from the first fractions of a second forward, through nucleosynthesis and recombination and the formation of the first stars and galaxies, all the way to the present moment. But the question of what caused the Big Bang, what gave rise to the singularity, what preceded it, what set the initial conditions, is still beyond the reach of our current physics. Some physicists propose that the universe arose spontaneously from a quantum vacuum, that quantum mechanics allows for the spontaneous creation of a universe from nothing, though nothing in. Quantum mechanics is not truly empty. Others propose that the Big Bang was the result of a higher dimensional brain collision, or a bounce from a previous universe, or something we haven't yet imagined. And some suggest that the question may not have an answer in the traditional sense, that causality and time themselves began at the Big Bang, making what caused it a question without coherent reference. We do not know. And perhaps, lying here in the quiet dark, that is enough for tonight. Some questions are beautiful, precisely because they are still open. Is the universe finite or infinite? It is one of the oldest and deepest questions in cosmology, and we still do not know the answer. The observable universe is finite. It is limited by the distance light has been able to travel since the Big Bang, which gives us a sphere roughly 93 billion light-years in diameter. But the total universe, everything that exists, including regions too far away for their light ever to reach us, may be much larger, or infinite. The geometry of the universe, as measured by the CMB and other observations, is consistent with being flat, and a flat, infinite universe is one theoretical possibility. But a flat universe that is finite, like the surface of a torus, a donut shape, in which you could travel in one direction and eventually return to where you started, is also consistent with what we observe. We simply cannot tell from the inside whether the universe extends forever or wraps back on itself, whether there are infinitely many stars beyond the edge of our observable horizon, or whether the observable universe is all there is, or nearly all. This question may be permanently unanswerable, a horizon we can never cross. And that is okay. Not every question requires an answer tonight. Some of them are simply there to be held lightly in the dark, a reminder that the universe is larger than our understanding and always will be. The horizon problem is the question of why the universe looks the same in every direction. Why regions of the CMB that are too far apart have ever been in causal contact nonetheless have almost exactly the same temperature. Regions on opposite sides of the observable universe are separated by 93 billion light-years. The universe is only 13.8 billion years old. Light travels at a finite speed. There has simply not been enough time for a signal to travel from one of those regions to the other. And yet their temperatures match to 1 part in 100,000. How? The standard answer is cosmic inflation. During the inflationary epoch, a tiny region of the early universe, a region small enough that all its parts had been in contact and had equalized their temperatures, was stretched to an enormous size, far larger than the observable universe. Everything we can see today was once part of that tiny, well-mixed region. The uniformity of the CMB is not a coincidence. It is a memory of a time before inflation, when what is now the observable universe was small enough to fit in a space much smaller than a proton, and all of it was in thermal equilibrium, sharing its heat equally in every direction. Inflation stretched that memory across the sky, and when we look at the CMB tonight, those ancient photons passing softly through everything, we are reading that memory with our instruments, reading the universe's earliest thoughts. The flatness problem is another puzzle that cosmic inflation helps resolve. It concerns the geometry of space, specifically whether the universe is positively curved like the surface of a sphere, negatively curved like a saddle, or flat like an infinite plane. The curvature of the universe is determined by its density relative to a critical value. If the density is exactly equal to the critical density, the universe is flat. If it's higher, it curves like a sphere. If it's lower, it curves like a saddle. What we observe is that the universe's density is extraordinarily close to the critical value, within a fraction of a percent. It is almost perfectly flat. And here is the puzzle. In a universe evolving under gravity without inflation, any tiny initial deviation from flatness would grow rapidly over time. If the universe had been even slightly curved at the moment of the Big Bang, that curvature would have amplified enormously over 13.8 billion years, producing a universe dramatically curved today, either collapsing long ago or expanding into cold emptiness long before stars could form. The fact that the universe is still flat today means that at the time of the Big Bang, it must have been flat to extraordinary precision. Perhaps to 1 part in 10? That seems impossibly fine-tuned. But inflation explains it. Any initial curvature would have been stretched away by the vast expansion, leaving the universe flat regardless of its initial shape. The ultimate fate of the universe is one of the grand open questions of cosmology, and the answer depends on dark energy, which we still don't fully understand. The most likely scenario, given what we currently know, is called the Big Freeze or heat death. In this scenario, the universe continues to expand forever, driven by dark energy. Galaxies drift farther and farther apart. Stars burn out one by one over trillions of years. New stars form more rarely as the supply of gas is exhausted. Black holes slowly evaporate through a quantum process called Hawking radiation. Eventually, in timescales that make the current age of the universe look like the blink of an eye, the universe reaches a state of maximum entropy. No temperature differences, no gradients of energy to drive processes, no information being processed, a cold, dark, featureless expanse of weakly interacting particles, growing ever more dilute in an ever vaster space. It is not a violent or dramatic ending. It is more like a slow, quiet fading, like the last embers of a fire, cooling in the dark, long after everyone has gone to sleep. There is something peaceful about it, in its own way, the universe ending, not with a bang, but with a long, slow, perfect stillness. Not unlike sleep, not unlike the quiet that is, even now, beginning to settle over you. About 200 to 300 million years after the Big Bang, the first galaxies began to form. They were not like the grand, luminous spirals we see in photographs today, orderly and majestic, with sweeping arms of stars. The first galaxies were small, irregular, chaotic things, dense clusters of the first stars, assembled by gravity in the densest nodes of the dark matter web. They collided with each other and merged, growing larger over time. Streams of gas fell into them from the cosmic filaments. More stars formed. Smaller galaxies were swallowed by larger ones. Over billions of years, through a process of hierarchical assembly, small things combining into larger things, the grand galaxies of today were built up from these humble early beginnings. The Milky Way itself is the product of billions of years of mergers and acquisitions, absorbing dozens of smaller galaxies throughout its history, growing steadily larger, accumulating stars and gas and dark matter from its surroundings. And it is not finished. The Milky Way is currently in the process of consuming several dwarf galaxies, and in about 4 billion years, it will collide and merge with the Andromeda Galaxy, its large nearest neighbor. Galaxies are not eternal, fixed structures. They are dynamic, evolving, constantly changing. Like everything else in this universe, never truly still, always in the process of becoming something new. The Milky Way Galaxy, our home, formed about 13.6 billion years ago, making it almost as old as the universe itself. It began as a small, dense cluster of the first stars, assembled in a concentrated region of dark matter in the early universe. Over billions of years, it grew through mergers with smaller galaxies, through the accretion of intergalactic gas, through countless generations of star formation and stellar death. Today, the Milky Way is a barred spiral galaxy about 100,000 light-years across, containing somewhere between 100 and 400 billion stars. Our Sun is an unremarkable, middle-aged yellow dwarf star located in one of the Milky Way's spiral arms, about 26,000 light-years from the galactic center. We are, in cosmological terms, in the suburbs, not at the center, not at the edge, but somewhere quietly in between. A pleasant, stable location where the density of stars is not too high for life to thrive, and not too low for the elements needed for life to have formed. The Milky Way stretches across the night sky as a faint, luminous band, visible from dark places on clear nights, a river of starlight that contains our entire history, every myth, every song, every act of love or courage or discovery that has ever happened on this planet, happened inside that band of light, inside that river, inside our ancient, still-growing home. Galaxy clusters and superclusters, the largest gravitationally bound structures in the universe, formed over billions of years through the slow accumulation of matter under gravity's patient pull. A galaxy cluster may contain hundreds or thousands of galaxies, all bound together by their mutual gravity, moving through the hot intergalactic gas that fills the space between them. The largest known supercluster, the Laniakea supercluster, is about 520 million light-years across and contains the Milky Way along with over 100,000 other galaxies. It is one of the largest known structures in the universe. And yet, even Laniakea is just one node in the even larger cosmic web, that vast network of filaments and voids that stretches across the observable universe, a three-dimensional tapestry of matter woven over 13.8 billion years by the combined action of gravity, dark matter, dark energy, and the initial density fluctuations of the Big Bang. When cosmologists map the large-scale structure of the universe, using surveys that measure the positions of millions of galaxies, the cosmic web emerges clearly. Bright filaments of galaxies surrounding enormous empty voids, the whole thing resembling, in photographs, the neural structure of a brain or the mycelial networks of a forest floor. The universe at the largest scale looks almost alive, almost organic, as if it too had grown from a single seed. Dark matter played an essential and irreplaceable role in the formation of the large-scale structure of the universe. Without it, the universe we know could not exist. In the early universe, ordinary matter was tightly coupled to radiation. Photons and particles interacted constantly, and this coupling prevented ordinary matter from clumping under gravity. The photon pressure smoothed out any density variations in ordinary matter before they could grow. Dark matter, by contrast, does not interact with light at all. It was free to begin clumping under its own gravity long before ordinary matter could, building up the dense scaffolding of the cosmic web during the long period when ordinary matter was still trapped in its dance with radiation. By the time ordinary matter finally decoupled from radiation, at the moment of recombination, the dark matter halos were already waiting, and ordinary matter fell into them, like water finding channels in rock. The galaxies formed where the dark matter was densest. The filaments of the cosmic web followed the dark matter skeleton. Every galaxy you can see in a photograph of the night sky is embedded in and shaped by an invisible halo of dark matter that outweighs all its stars. Dark matter is the hidden architecture of the universe, the invisible scaffolding on which everything visible has been built, like the frame of a house, invisible inside the walls, supporting everything from within. Our solar system, the sun, the 8 planets, their moons, the asteroids and comets, formed about 4.6 billion years ago from a slowly rotating cloud of gas and dust called the solar nebula. This cloud was made of hydrogen and helium from the Big Bang, enriched with heavier elements, carbon, oxygen, silicon, iron, that had been forged in earlier generations of stars and scattered into space by stellar winds and supernova explosions. Under gravity, the cloud slowly contracted. It began to spin faster as it collapsed, the way a figure skater spins faster when they pull their arms in. The center grew denser and hotter until it ignited as a star, our sun. The remaining material spread into a flat disk around it, and within that disk, tiny grains of dust stuck together, growing gradually into pebbles, then boulders, then planetesimals, then planets. The process took tens of millions of years. The Earth formed about 4.5 billion years ago, and the first signs of life appear in the fossil record about 3.5 to 3.8 billion years ago. From the Big Bang to the first living cells took about 10 billion years. From the first living cells to you took another 3.8 billion years. You are the product of a 13.8 billion year chain of events, each link following from the last. From the singularity of the Big Bang to the warmth of this present moment. What an extraordinary chain it has been. Every heavy element in the universe, every atom of carbon in your body, every atom of oxygen in the air you breathe, every atom of iron in your blood, was forged in the nuclear furnaces of stars. The Big Bang produced only hydrogen, helium, and a whisper of lithium. Everything else on the periodic table, the 90-odd naturally occurring elements heavier than lithium, was created by stellar nucleosynthesis over billions of years in the cores and explosions of stars. Carbon was forged in the helium-burning cores of red giant stars. Oxygen was made in massive stars during their final stages. Iron accumulated in the cores of massive stars until its formation could no longer release energy, triggering the catastrophic collapse of the star and the tremendous explosion of a supernova. Gold and uranium and the heaviest elements were created in the violent, exotic conditions of neutron star mergers. 2 incredibly dense stellar corpses spiraling together and colliding in a cataclysm that briefly outshines a galaxy. You are not simply made of atoms. You are made of atoms that were cooked in stellar cores over billions of years and scattered across the galaxy by stellar explosions. The calcium in your bones was once part of a star. The nitrogen in your DNA drifted through space for millions of years before finding its way to Earth. You are, in the most literal and beautiful sense, a child of the cosmos, a product of the universe knowing itself. The oldest known stars in the Milky Way are nearly as old as the universe itself, about 13.6 billion years old. They formed in the earliest epoch of galaxy formation, from the pristine hydrogen and helium of the Big Bang, barely enriched by any previous stellar generation. These stars are part of the Milky Way's halo, a roughly spherical distribution of old stars that surrounds the flat disk of the galaxy, remnants of the ancient, chaotic mergers that assembled our galaxy in its youth. Finding and studying these ancient stars is one of the great challenges and triumphs of modern observational astronomy. By analyzing their light, measuring the abundances of different elements in their spectra, astronomers can read the chemical history of the early galaxy. Stars that formed very early have almost no heavy elements. Stars that formed later are progressively more enriched. The chemical evolution of the galaxy is written in the composition of its stars, the way the growth rings of a tree record the history of the years it has lived. And the oldest stars, those pale metal-poor relics drifting in the galactic halo, are our direct connection to the Big Bang. They condensed from the same primordial hydrogen and helium that emerged from the first moments of the universe. They have been burning steadily and quietly for 13.6 billion years. They are still burning now, somewhere above you in the dark beyond the dark. Supermassive black holes. Black holes with masses millions or billions of times that of the Sun were found, to cosmologists' considerable surprise, already existing in the very early universe. Some of these behemoths appear to have been fully formed within the first billion years after the Big Bang, a timeline that is extremely difficult to explain with conventional models of black hole growth. Ordinarily, black holes grow by accreting matter, pulling in gas and stars from their surroundings over long periods of time. But to grow to a mass of 1 billion suns in less than 1 billion years requires either starting from an unusually massive seed or growing at rates close to the theoretical maximum, continuously, without interruption. Neither scenario is easy to arrange, and the question of how the earliest supermassive black holes formed so quickly is one of the most active and intriguing puzzles in modern astrophysics. We know they existed. We can see them as quasars, blazing with the light of accreting matter, visible from billions of light years away and billions of years back in time. We just don't fully know how they got so big so fast. The universe, as usual, is more complex and more surprising than our models anticipated. Every answer opens new questions. Every solved puzzle reveals a deeper one beneath. The universe is not in the habit of running out of mysteries. The James Webb Space Telescope, launched in December 2021 and delivering science since 2022, has transformed our view of the early universe. It observes in infrared light, wavelengths invisible to the human eye, which is essential for seeing the most distant galaxies, whose light has been redshifted by the expansion of the universe into the infrared part of the spectrum. Webb has detected galaxies that formed within the first few 100 million years after the Big Bang, earlier than many models predicted, and often more massive and more structured than expected. It has found evidence of galaxies already well formed just 300 million years after the Big Bang, raising fascinating questions about how quickly the first galaxies assembled. It has observed the spectra of early galaxies, measuring their chemical compositions, their star formation rates, their ionization states, and it has done all of this with a clarity and depth that no previous telescope could achieve. Each new set of Webb images is, in a very real sense, a deeper reading of the Big Bang's legacy, a more detailed examination of the first chapters of cosmic history. We are living in a golden age of observational cosmology. The universe's earliest moments are, for the first time, directly visible to us, shimmering in the infrared, billions of light years away, billions of years in the past. Quietly, patiently, Webb is reading the universe's oldest pages. Every single atom in your body, every proton, every neutron, every electron came from the Big Bang or from a star that was born because of it. The hydrogen atoms, the most abundant in your body, are truly ancient. They were forged in the first 3 minutes after the Big Bang, in the brief hot window of nucleosynthesis, and they have been drifting through the universe ever since. Through gas clouds, through the interstellar medium, through the solar nebula that formed our sun, through the oceans and atmosphere of the early Earth, through geological cycles and biological processes, until eventually they found their way into the molecules of your body. Those hydrogen atoms are 13.8 billion years old. They are older than the Earth, older than the Sun, older than the galaxy. They have been part of stars and comets and ancient oceans, and living creatures too numerous to count. And now, for this brief moment in cosmic time, they are part of you. part of the particular, temporary, extraordinary arrangement of matter that is a human being, lying quietly in the dark on the verge of sleep. You borrowed your atoms from the universe. One day, you will return them. They will go on to be part of other things, other creatures, other worlds, other chapters of the story. But tonight, they are yours, and you are theirs. The hydrogen in your body is 13.8 billion years old, not metaphorically, not approximately, literally, directly, traceable to the Big Bang itself. When cosmologists say that human beings are made of stardust, they are being precise. The heavier elements in your body, carbon, oxygen, nitrogen, calcium, iron, were indeed made in stars, but the hydrogen was there before any star existed. It condensed out of the hot plasma of the early universe during Big Bang nucleosynthesis, before the first galaxy formed, before the first star ignited, before the solar system was even a whisper of a possibility. Those hydrogen atoms spent billions of years drifting through the void, slowly gathering into clouds under gravity, becoming part of nebulae and stars, cycling through generations of stellar birth and death, until finally, about 4.5 billion years ago, some of them ended up in the swirling disk of gas and dust that would become our solar system. Some found their way to Earth. Some became part of the early oceans, and over billions of years of biological evolution, some of them became part of the molecular machinery of life, and eventually part of you. You are, in the deepest sense, as old as time. Your substance is primordial. When you breathe in, that slow, gentle breath you are taking right now, on the edge of sleep, you are inhaling atoms that have been traveling through the universe since the beginning. Welcome them home. The light released at recombination, those photons that have been traveling for 13.8 billion years and are now the cosmic microwave background, is still reaching Earth today. It has been traveling continuously since the moment the universe became transparent, 380,000 years after the Big Bang. Every second, CMB photons pass through every square centimeter of space, including the space above your bed right now, and the space inside the room around you, and the space within your body. They travel at the speed of light, as all photons do. They carry within them information about the temperature and density of the universe at the moment they were last scattered. They are the oldest light that can ever reach us, the ultimate limit of our observational reach back in time. Beyond the CMB, the universe was opaque, and no light can come to us from that earlier era. The CMB is the cosmic horizon, the edge of the visible universe in time, and it surrounds us softly and completely from every direction. Right now, ancient light from the Big Bang is passing through you. You are immersed in it. You have always been immersed in it. You will be immersed in it for every moment of your life and long after. The Big Bang never really ended. Its light is still arriving. If you took all the matter in the observable universe and compressed it back to the density it had at the time of the Big Bang, packing all those billions of galaxies, all those hundreds of billions of trillions of stars, all that dark matter, all that gas, into a space as small as a golf ball, it would be a golf ball of infinite temperature, infinite density, of such impossible compactness that no concept in ordinary experience can capture it. The observable universe, which stretches 93 billion light-years in diameter and contains more stars than there are grains of sand on all the beaches of Earth, was once smaller than a proton, much, much smaller. All of it, every galaxy, every nebula, every atom, every particle of dark matter, everything that has ever existed or ever will exist within the range of our observation, all of it, compressed into a space smaller than the nucleus of a single hydrogen atom. It is perhaps the single most mind-bending fact in all of science, and yet the mathematics supports it. The evidence points to it. The universe was once that small, and then it expanded, and it kept expanding for 13.8 billion years until it became this, a vast, dark, star-scattered night, and a person lying quietly in a bed, breathing slowly, feeling the weight of their body on the mattress, very nearly asleep. The Big Bang did not happen at a specific location in space. It happened everywhere. This is one of those ideas that takes a while to really settle in. The mind keeps wanting to find a center, a source, a place you could travel to and say, here, this is where it all began. But there is no such place. Before the Big Bang, there was no space. Space itself was created at the moment of the Big Bang, and as it expanded, every point in it expanded equally away from every other point. There is no center to a sphere that is being inflated. Every point on its surface is equally the center, in the sense that every point sees every other point moving away from it. The universe has no edge and no center. It is the same in its large-scale structure, in every direction, and from every location. This property is called the cosmological principle. The universe is homogeneous, the same density everywhere on large scales, and isotropic, the same in all directions. It is one of the foundational assumptions of modern cosmology, and it is confirmed by observations of the CMB and the large-scale distribution of galaxies. You are not at the edge of the universe. You are not near the center of the universe. You are in the middle of the universe in the only sense that counts, because every place is equally the middle. Rest in that. You are not peripheral. You are not displaced. You are exactly where you have every right to be. Albert Einstein published his general theory of relativity in 1915. A theory that described gravity not as a force acting at a distance, as Newton had proposed, but as the curvature of space-time caused by mass and energy. It was one of the most profound intellectual achievements in the history of science. And almost immediately, when physicists began applying Einstein's equations to the universe as a whole, they found that the equations did not support a static universe. They predicted a universe that was either expanding or contracting, a dynamic, evolving cosmos, not the eternal, unchanging background that most scientists of the time assumed existed. Einstein was troubled by this. The idea of an evolving universe seemed philosophically unsatisfying to him. He wanted the universe to be eternal and stable, and so he added a term to his equations, a cosmological constant, a kind of anti-gravity that would balance the tendency of the universe to contract, holding it in a static equilibrium. When Hubble's observations confirmed in 1929 that the universe was indeed expanding, Einstein famously removed the cosmological constant and called it his greatest blunder. But the story doesn't end there. When dark energy was discovered in 1998, the mysterious force accelerating the expansion of the universe, physicists realized that Einstein's cosmological constant was actually the best available mathematical description of dark energy. His greatest mistake turned out to be, in a sense, his greatest insight. The universe had been telling him something true, and he had put it in his equations and then crossed it out. The Big Bang theory remains, by an enormous margin, the most well-supported scientific model for the origin of the universe. Its predictions, the expansion of the universe, the cosmic microwave background, the abundances of light elements, the large-scale structure of the cosmos, have each been confirmed independently by multiple different methods, using multiple different instruments, by scientists from different institutions and different countries over many decades. No other cosmological model comes close to matching the breadth and precision of its confirmed predictions. This does not mean it is complete. There are still profound mysteries. The nature of dark energy, the mechanism of inflation, the cause of the matter-antimatter asymmetry, what happened at and before the singularity. These are genuine open questions, and science does not pretend otherwise. But the core picture, a universe that began hot and dense, that has been expanding and cooling for 13.8 billion years, and in which the structures we observe today grew from tiny primordial fluctuations, is as well established as any idea in science. It is the story of where we came from, and it is a story of extraordinary beauty, more beautiful in many ways than any myth or legend, because it is true. It is written in the light of ancient stars, in the warmth of ancient photons, in the atoms of your body, and you carry it with you, always. Even now, even in sleep, carry it gently and rest, and so quietly, here we are, at the end of the universe's story for tonight, and at the beginning of your sleep. You came from something unimaginably vast and ancient. Every atom in you has been on a journey of almost 14 billion years. You are not small. You are not accidental. You are the universe, briefly gathered into a form that can wonder about itself. And now that wonderful form is tired. It is warm. It is safe. The stars are above you, and the ancient light is passing through you, and the universe is still expanding. And you don't need to hold any of it right now. You can simply let it all go. Let your breath slow. Let your thoughts soften at the edges. Let the quiet take over. Sleep now. The universe will still be here when you wake.